Hello everyone, welcome back to the Life Science lecture series. Welcome back to the channel. So I'm today excited to share with you because and learn with you because today we're going to be diving into one of the most exciting and fascinating topics in genetics, that is chromosomal aberrations. Tiny changes that happen in our chromosomes. They can make a big difference in how we grow and develop. We'll uncover what happens when chromosomes break, rearrange, or when they miscount, and how these mysteries they help doctors to diagnose conditions and to support families and push the science forward. So let's move on and decode the science together. Okay, so yeah. So chromosomes they are like master pages of a genetic instruction manual. So just like a book can have a tear or repeat, flip, they can get glued to the wrong chapter. These changes happen. This is what chromosomal aberration is. A small deletion can remove important instruction. Duplication can repeat them. Inversion can flip them. And translocation can swap segments between chromosomes. So each tiny change happening in structure, it can shape how a person develops, grows, or functions, making chromosomal aberrations one of the most exciting and fascinating chapters in genetics. Chromosomes face constant wear and tear. They can every cell division requires billions of DNA letters to be copied, and even a tiny slip can cause break. Sunlight, chemicals, radiation, metabolism can all lead to DNA breaks, and sometimes the repair mechanism is not just correct. Meiosis, where the sex gametes are formed, chromosomes swap pieces, but mistakes like unequal exchange or faulty reattachment can happen. These errors create deletions, duplications, and all the variations that you see. So, though these variations might be harmful, but sometimes it can be beneficial to drive evolution as well. So, now we'll move on to the chromosomes. Now, they might look very simple on when you see them, but they have more. They tell you more. Their shapes they tell you more powerful stories. Just by shifting the centromere a little bit from the middle to the edge, maybe you can have you can get different chromosome types of chromosomes. So shapes of these chromosomes they decide how the chromosomes should move, how they should divide, and also sometimes misbehave as well. Now we'll move on to chromosomal aberrations. Chromosomal aberrations or chromosomal mutations, they are like editing mistakes happening to our DNA blueprint. So sometimes a page can be missing, repeated, flipped, or they can move. Every small change that happens, they change how our genes work. These changes matter. Why? Because they affect your development, fertility, genetic disorders, cancer risk, and even evolution. So chromosomal aberrations fall into two big categories: structural aberrations and numerical aberrations. Structural aberration is when a chromosome's shape changes, the structure changes. Numerical aberration is when the number of chromosomes change. Two groups, but they explain almost every major genetic disorder which we see. Structural chromosomal aberrations happen because a chromosome breaks and the pieces rejoin in a wrong way or they don't rejoin at all. Four major outcomes are there because of this change happening to the structure. You can have deletion, where a piece gets lost, duplication, where a piece repeats, inversion, where a segment or piece flips, and finally translocation, where segments are exchanged. Moving on to our first type of structural chromosome aberration is deletion. Deletion is when a piece of chromosome breaks and is completely lost. It's like removing a whole chapter from a book. So the story still continues, but the important instructions are still missing, right? Deletions happen when a chromosome breaks in two places and the middle segment doesn't reattach. The remaining ends join together, leaving out missing pieces. So if you see this diagram here, you have A, B, C, D, E, F. So if there is a break in between A, B, C and D, E, F, so in that case, the D, E segment will be removed. Okay. Why does why does deletion occur in the first place? What are the reasons that lead to deletion, or what causes deletion? So deletions happen because of errors happening during meiosis when chromosomes fail to align or exchange pieces properly due to unequal crossing over where the chromosome gets extra material and the other one might lose another lose material. DNA damage due to radiation or chemicals, chromosomal breaks, chromosome breakage which happens. This so the repair doesn't happen correctly. So most deletions that happens in biology, okay, are not good because it's not very easy to paste things back perfectly, and biology doesn't do it in a very perfect way. So what are the effects of deletion? So the effect or impact of it depends on how big the missing segment is and which genes were in it. So small deletions may go unnoticed, but the larger ones, they can cause major developmental issues. Sometimes it can lead to essential genes going missing. Effects can include loss of important genes, so that means lead to reduced protein production. You can have developmental delays or physical abnormalities, or you can have genetic disorders like cry-to-chat 5p deletion. So what when genes go missing, their functions also vanish, and the body has to grow and work with incomplete instructions. Here you can see, right, how deletion occurs. Now imagine a tiny piece that is missing from the tip of chromosome 5, especially the short arm called 5p. So the missing segment leads to a condition which has a very unusual and a memorable clue as well. Cry-to-chat syndrome. Cry-to-chat is called, why is it called as cry-to-chat? Because the newborns, they have a distinctive and high-pitched cry that sounds like a kitten meowing. So it's known as cry of the cat. So this happens because there is genes missing in the voice box for formation of voice box and nervous system. The condition is more than just a cry. What exactly happens genetically is the piece, a section of chromosome 5p gets deleted. So the size of the deletion varies. Based on that, the symptom also varies. So it is not usually inherited. Most cases it happens by chance during early embryo development. Some of the key features of cry-to-chat is the cry cat like a cry because of undeveloped voice box and altered brainstem. Small head will be the small head formation, which is known as microcephaly. Missing genes, they can affect the brain growth. They can have distinct facial features, wide set eyes, slow motor and cognitive development. Missing genes, they affect the neuron formation, low birth weight and feeding difficulties. So chromosome 5 deletion, it's like you have a detailed instruction manual. So if a whole paragraph is missing from the first page, the machine, the developing baby, it can still be built, but some parts work differently or they might need extra support. Why? So early support will definitely help here. Therapies and children gain skills and improving their communication. Okay, this can help them. Now moving on to the second type of structural chromosomal aberration, duplication. We did deletion, now it is duplication. Duplication, as the name suggests, this is where a segment has more than one copy. So one copy, the one segment or one section is copied twice. So you have extra information now, right? So how does it happen? It occurs again due to crossing over, where chromosomes exchange pieces. If the exchange is unequal, one chromosome gains extra material, whereas the other loses it. One example is that if you have a segment like a chromosome A, B, C, D, then it can become A, B, C, C. So the C segment is repeated here. So why does deletion occur, or what causes duplication? Not deletion. What causes duplication, or why duplication occurs? So duplication occurs because there is unequal crossing over, as I told you, during meiosis, replication errors where DNA copies a region twice. There are transposable elements where it goes and inserts extra segments, chromosomal breaks, and faulty repair. Duplication, there are three types or three forms of duplication. So there is tandem duplication. The duplicated segment appears right next to the original one. Reverse duplication. The duplicated segment is reversed. Displaced duplication. The duplicated segment occurs elsewhere on the chromosome, same or different arm. And now what are the effects of duplication? So it depends on how big the duplicated region is and which genes are in it. So extra copy means that there are extra dosage, gene dosage. That means too much protein production. So that can affect your normal development. Some common effects are developmental abnormalities, learning or growth delays, genetic syndromes. So sometimes duplication is also beneficial in evolution. So extra copies means you have new functions to evolve. So that, okay. Now, one of the conditions is MCP2 duplication syndrome. This happens because a small segment of the X chromosome, the region that contains the MCP2 gene, is accidentally copied twice. So the duplication occurs because due to errors happening during the formation of egg or sperm or cells or during early embryo. So what happens is that sometimes the X chromosome, it forms extra loops or misaligns happen with its pair. So when such error happens, the cell will try to repair it. And the region, so while repairing, it mistakenly adds an extra copy instead of keeping just one. This leads to too much of the MCP2 protein, which disrupts the brain and immune development and the function. So in many families, the duplication is inherited from mother, who carries the change without symptoms because she has another normal X chromosome. So boys who have just one X chromosome, they show the syndrome more strongly. So the children who have the MCP2 duplication, they'll have low muscle tone, developmental delays, frequent infections, feeding difficulties, and sometimes seizures as well. Now moving on to the third type of structural aberration is inversion. So what is inversion? Inversion is when a chromosome breaks in two places and the piece in between flips upside down and it reattaches. Okay, so here it's like taking a story, a sentence from a story, turning it backwards and putting it back in the same spot, but in a different direction, a wrong position basically. So inversions occur, so a chromosome breaks into a two. Okay, the middle segment rotates 180 degree and the end rejoins back around the flipped piece. So the chromosome keeps all its genes but in the wrong orientation. Why does it happen? Again, the same reasons like DNA breakage, errors during crossing over, okay, errors happening, unequal crossing over, errors for during chromosome breaks, radiation, etc. So the chromosome basically gets cut and the cell pastes it back, but in a reversed order. Now, there are two types or forms of inversions, paracentric and pericentric. Paracentric is where the centromere is not included along with the inversion. So the flipped segment lies on one arm only. So example ABCD, it becomes ABDC. In pericentric inversion, the centromere is included. So the breaks happen on both arms. Example is if you have ABC with the centromere and DEF, that turns into ABD centromere and CEF. So a simple way to remember is that para means beside the centromere and peri means around the centromere. Now, what are the effects of inversion? Now, because the genes are not lost, they're still there. So people with inversion are healthy. But problems happen during meiosis, during the egg and sperm formation. So inverted regions, they pair incorrectly. Crossing over inside the inversion creates unbalanced chromosomes. This can lead to miscarriages, infertility, children with duplications or deletions, structural disorders. Inversions are harmless to people, but they can be risky for the offspring. Now let's move on to a condition that is caused due to inversion, that is hemophilia A. Hemophilia A is a bleeding disorder where the blood can't clot properly because one of the important protein, that is factor 8, is missing or it doesn't work properly. It's like trying to build a brick wall without cement, with the cement actually. So without cement, you cannot make a structure, right? The structure will not hold without the cement. That's just how it is. So how does it occur? It happens because the F8 gene, which is factor 8 gene on the X chromosome, is changed or it gets damaged. The gene normally makes factor 8. So when the gene is faulty, factor 8 levels drop. So clotting can't happen quickly, and it is so that leads to prolonged bleeding phenotypes. So why it occurs primarily because hemophilia A occurs because of inherited mutations happening in F8 gene or spontaneous mutations happening during egg and sperm formation, sometimes because of large inversions within the F8 gene itself. Because it's X-linked recessive disorder or X-linked recessive condition, boys, they just have one X chromosome only. They have X and Y, right? So they have only one X chromosome. So they show the disease more profoundly, or phenotypes more profoundly than girls. So girls are often carriers because they have one more X chromosome. Boys, they only have one X chromosome. So if that single X carries this particular mutation, so the body can't make enough factor 8. What happens because of that? So because there is no factor 8, the clotting chain breaks. Blood continues to leak longer than normal, especially in the joint and muscle. So what are the effects of hemophilia A? So there will be prolonged bleeding from cuts or injuries. Spontaneous bruising will be there, pain will be there. So even if a small minor injury is there, this can cause major bleeding because your clotting system can't function or they can't switch properly. Now fourth and final structural aberration is translocation. Translocation is where you have two different chromosomes and segments are exchanged between each other. So it's like trading paragraphs between two different books. So the genetic material is, or the content is still there, but it's there in the wrong place. It's there in the wrong location. Now, how does it happen? It happens because of chromosomes break and the loose pieces, they attach to the wrong places or wrong partner. So this mix-up which happens during meiosis when chromosomes pair up and recombine. So if the alignment is wrong, then the pieces swap with the wrong chromosomes. So in short, you can say that breaks happen in chromosome, mix-up happens, and then rejoin in wrong places. Now, why does it occur? It can occur because of error in DNA repair, radiation exposure, viral insertions, or misalignment during crossing over can cause segments to be exchanged. Chromosomes continue to communicate. They communicate a lot through cell division, and sometimes the exchange goes wrong and there is wrong information as well. Okay, the exchange that is you get wrong information are exchanged while cell division sometimes. Now, types of translocation. So there are three types of translocation. First is reciprocal translocation. This is the most common type of translocation. Here, the two non-homologous chromosomes, they swap segments between each other. The genetic material stays balanced. Okay, there is no gain or loss. Carriers are usually healthy, but they will have risk of imbalanced gametes. They might have miscarriages or disorders, the particular gametes. Coming on to the second type is the non-reciprocal translocation. Here, here a piece from one chromosome moves to another without getting anything back. Causes unbalanced gene dosage. So the effect can be more big here because okay. And finally, the third type, which is a special type, is Robertsonian translocation. Robertsonian translocation happens only in acrocentric chromosomes like chromosome 13, 21, etc. So the long arms, they fuse and they form one large chromosome and a tiny fragment is lost. Translocation of such kind is associated with Down syndrome. So two long arms, they join, one chromosome is lost, so totally the count of chromosomes becomes 45 instead of 46. Okay. Now, what are the effects of translocation? So, effects of translocation, it is based on the gene dosage change which happens. So, carriers can look completely normal, but they can have repeated miscarriages. They can have infertility issues, children with genetic syndromes, sometimes cancers as well. Translocations are silent in one generation, but they can be loud in the next generation. As you see here, right? A segment has been exchanged. This is this is an example of reciprocal translocation. Now, one exciting feature or an exciting feature of translocation is role with evolution. So humans, chimpanzees, gorillas, orangutans, we all share a common ancestor. But there is one difference that we all have. That is difference is there in our chromosomes. Humans have 46 chromosomes. Chimpanzees or orangutans all have 48 chromosomes. So what exactly happened? Why is there a change in the chromosome number exactly? So that will be because at some point in our evolutionary history, two smaller acrocentric chromosomes fused together, forming what we know as human chromosome 2. This event is called Robertsonian translocation, where long arms of two chromosomes join and act as one. It didn't remove any important genetic material, it just reorganized it. This fusion is one of the strongest pieces of evidence which humans and great apes share a common ancestor. The matching banding patterns like DNA fingerprints reveal that human chromosome 2 is made from the same pieces found separately in chimpanzees, gorillas, and orangutans. So a single chromosome fusion, like Robertsonian translocation, had helped to shape the species that we have become today. And so this is really great and fascinating. Now moving on to one of the uh, conditions or disorders that is caused due to translocation or primarily you can say reciprocal translocation is chronic myeloid leukemia. So here, what happens? The bone marrow you can imagine it's like a factory. It makes up blood cells, and normally it follows a rule book, but producers just write the number of white blood cells to defend the body. But in certain cases, like chronic myeloid leukemia, a tiny chromosome swap creates a huge change. A piece of chromosome 9 and a piece of chromosome 22 accidentally exchange the places. This mistake forms the famous Philadelphia chromosome, a fusion gene between BCR and ABL. This fusion gene leads to multiplication of white blood cells indefinitely without stopping. As a result, the body becomes flooded with abnormal white blood cells, pushing out the normal ones needed for your immunity and oxygen transport. So the cause of CML is not infection or lifestyle. It's a molecular glitch that happens in your blood cell formation, blood cell production into uncontrolled growth. Now let's move on to the next chapter, which is numerical aberrations. Now every human cell should carry normally 46 chromosomes, a perfect set, like the correct number of chapters in a book, right? But sometimes the numbers change. There can be too many or too few chromosomes. These changes are called numerical chromosomal aberrations, when the chromosome count goes wrong. So two major types, aneuploidy and polyploidy. Aneuploidy is where there's a missing or extra chromosomes. So it's like a book which has one chapter removed or duplicated. So aneuploidy happens when chromosomes fail to separate properly during meiosis. The mistake is called as non-disjunction. So example for aneuploidy is very common is Down syndrome, trisomy 21 with extra chromosome, monosomy X, Turner syndrome with the missing chromosome. So aneuploidy is equal to one or few chromosomes which are miscounted. Then the second is the polyploidy. Polyploidy, here there is extra full sets instead of losing just one chromosome. So the entire set gets duplicated here, like getting an extra copy of the whole book. Common in plants, makes fruits bigger and seedless. Triploidy you have with three sets. Tetraploidy you have with four sets. Polyploidy is equal to whole sets multiplied. So why do numerical aberrations occur? They occur because of non-disjunction, which is the uh, primary cause of aneuploidy. Chromosomes, they don't separate properly. Errors happen in spindle fibers. Age is a big factor here, maternal age especially. Failure in cell cycle checks. But the major issue is leading to non-disjunction. So the effects due to numerical aberration is that because the gene dosage changes, numerical aberration often lead to developmental disorders, pregnancy loss, infertility, and sometimes beneficial traits for plants and evolution. What looks like a simple counting error, they can lead to a big change into the entire life. Numerical aberrations occur when cells have a wrong number of chromosomes. Aneuploidy, they affect a single chromosome, just one chromosome like trisomies. And monosomy, just one single chromosome is affected here. Polyploidy multiplies whole sets of chromosome. They are common in plants, they are very rare in humans. Now coming on to the okay. So sometimes during cell division, chromosomes don't separate out correctly. One cell may have too many and others get too few. And this is what you have aneuploidy. So when a single extra or missing chromosome can change, they can change development in big ways. Because chromosomes carry thousands of important genes, which are okay. So that is why aneuploidy is a big um, one of the primary leading cause of miscarriages and all disorders. Okay, so what are the types of aneuploidy? First is nullisomy. Okay, so there are many, but we'll just stick on to four. So nullisomy is where two whole set, the whole two pairs of chromosome, they go missing. So you have basically two entire chapters are missing basically. So the embryo, so the is usually very lethal. So embryo will not survive because a lot of information is missing here. And this is how you represent it. The formula 2n minus 2. So the next is monosomy. Monosomy, you have one missing. So one chromosome pair is lost. So you have one chromosome only. So the remaining copy has to work alone, which is not enough. So example one very famous or common example is Turner syndrome 45X. So the formula is 2n minus 1. Okay, so one chapter is missing and the story struggles to continue. Trisomy. Trisomy is one extra chromosome. So a chromosome shows up in three instead of two. Okay, so instead of having a pair, you have three. So that means there are too much of gene dosage. So that disrupts the growth. But some trisomies are compatible with life. Example is Down syndrome. Then, so you can say, so one extra chapter and life changes. And finally, you have tetrasomy, where there are two extra copies. Okay, so both copies are which are there, they get duplicated. So we have four instead of two. This is very rare. It occurs mostly in sex chromosomes sometimes. So we have conditions like 48, 4x's. Okay, so here the formula is 2n plus 2, but trisomy is 2n plus 1. Fine. Now let's move on to aneuploidy in humans. So human life depends on the perfect chromosome count, that is 46. But during meiosis, when eggs and sperms are made, chromosomes they should separate exactly. But sometimes that doesn't happen, and that mistake in separation is called non-disjunction. Okay, and that tiny counting error changes everything. Okay, so here in non-disjunction, the pair will refuse to separate. So one cell will have two copies and the other cell will have none. If a gamete like that, if a gamete forms a baby, then the child will have extra or they'll have missing chromosomes, a condition known as aneuploidy. Why does aneuploidy occur? Most of the time it happens because by chance during meiosis the spindle fibers flip or there is a chromosome that lingers too long and separation fails. Age increases the risk especially for mothers because woman's eggs are as old as she is. The machinery that holds chromosomes together weakens over time, making non-disjunction more likely. So older the eggs, higher chances of non-disjunction and higher the chances of aneuploidy. Why does aneuploidy cause genetic disorders? Chromosomes, they carry thousands of genes. Extra or missing chromosome means that there are either too much or too little protein. The balance of development shifts and the body responds. Example like extra 21 leads to Down syndrome. Missing X lead to Turner syndrome. So aneuploidy changes the gene dosage and it changes the development as well. So why does aneuploidy cause miscarriages? Half or around 50% of the miscarriages are because of aneuploidy. Most embryos with big chromosome mistakes, they cannot survive early development. The genetic imbalance is just too great. It's too great, so you can't allow it can't survive. Nature checks every embryo, only the stable one survives and they are allowed to continue. Aneuploidy isn't just always inherited. Sometimes cells lose control also later in life. Cancer can also be cause cancer cells. They often have chromosomes with gains and losses. So this helps them to like grow faster, escape signals, and to spread faster as well. So in cancer, the aneuploidy is like a weapon. So it helps them to fuel the uncontrolled growth. Now moving on to now sex chromosomes are very special. They are very special because unlike autosomes, they already have a flexible system. So males have XY, so they have one X and one Y. Females have two X chromosomes, so they shed one X chromosome. So the body works by adjusting the dose of genes on the X chromosome. Okay, so in this case, so losing or gaining a sex chromosome is much more less harmful than changes happening to autosomes, where even one extra change can cause lethal imbalances. Sex chromosome aneuploidies are actually the most common aneuploidies in living humans. Why are they more tolerated compared to autosomal aneuploidies? The reason is X inactivation in females. So one X automatically turns off in females, so extra copies they don't overwhelm the cell. The Y chromosome that is there in males, they have only few or very small number of genes. Extra Y rarely causes any issues that are severe. X chromosome, sex chromosomes, they have very few essential genes required for development. So there can be imbalances happening to the sexual development, but there won't be problems for surviving. So individuals often will survive, but they will have reproductive or physical differences. So two common and major conditions that is due to aneuploidy in sex chromosome is Klinefelter syndrome and Turner syndrome. Turner syndrome is 45X. There is a loss in one of the X chromosome in females. So one X chromosome is missing here. So you have 45 and X. You have just one X chromosome. So girls will have a shorter and webbed neck here. They'll have a heart issues. They'll have infertility issues. Okay. But their intelligence is normal. They just missed some instructions for growth and ovaries. Okay. So most X monosomies, they don't survive. Turner syndrome is a rare exception to this case. Turner syndrome is nature proving a single X can still fulfill life properly. Now moving on to the second type is second condition is Klinefelter syndrome, which is 47XXY. Here the boys will have an extra copy, extra chromosome X, and the body doesn't know which X to turn off completely. So as the growth happens, as they grow, they will become taller and they'll have less body hair. They'll have reduced fertility. Hormonal, they'll develop breast because there is a shift in hormones, so they start developing breast. Many boys, they don't even know it until they reach adulthood actually. So sorry. So one X chromosome, they soften the masculine traits without removing intelligence or personality. Now moving on to autosomal aneuploidy. Autosomes are the ones that carry genes that are required for development of uh, like core uh, like core organs like heart, brain. All development is occurs in your autosomes. So any change happening, so if one of these chromosomes are missing or there is an extra gene extra, that means the gene dosage will change dramatically and the body will struggle to grow and develop normally. So autosomal aneuploidy is severe because autosomes carry essential genes. And why is that autosomal aneuploidy is less common than sex chromosome aneuploidy? One reason is that autosomes, they're just one. So they don't have any X like a backup system like X inactivation. So they contain thousands of crucial genes. Even small dosage shift, they lead to major developmental failure. So while embryos can form, development cannot continue. Why do most autosomal aneuploidies cause early miscarriage? So when the gene dosage imbalance is just too large, the embryo cannot survive the earliest weeks. Nature performs the quality check and checks out and almost all embryos that have monosomy or trisomy conditions, they are silently lost before a woman even knows she's pregnant. Uh, and more than 95% of autosomal aneuploidies are stopped before birth. So why do some aneuploidies, autosomal aneuploidies, like chromosome, like Down syndrome, survive? Or like trisomy 21, how do they survive? It's because some autosomes, they have small or they carry fewer genes. So an extra copy causes problems, but life remains possible. So these chromosomes, they have lighter genetic load, so the body manages, but they will have distinctive developmental effects. The smaller the chromosome, the greater is the chances of survival. Now, of the few autosomal aneuploidies that are there that reach birth, is one of the few that actually reach birth is Down syndrome, trisomy 21. So Down syndrome or trisomy 21 is the most compatible with life when it comes to autosomal aneuploidy. Now let's see how extra chromosome 21 shapes development and behavior. Down syndrome happens when a person has 3 copies of chromosome 21 instead of 2, a condition called trisomy 21. Chromosome 21 carries genes important for brain development, heart function, muscle tone, and facial features. When an extra copy occurs, these genes work a little differently, leading to the characteristic Down syndrome conditions and traits. People with Down syndrome, they may learn more slowly and they may need extra support medically and developmentally. But they also show empathy and strength, warmth, and joy. A unique ability to connect, they have a unique ability to connect with people around them. Down syndrome reminds us that every chromosome change that happens, but that doesn't actually define a person's worth, abilities, or identity. Why does Down syndrome occur? During meiosis, chromosomes fail to separate due to non-disjunction. This creates a gamete with 2 copies of chromosome 21. So when fertilized, the embryo will have 3 copies of chromosome 21. This is how chromosome or Y chromosome Down syndrome occurs. Now there are various ways which Down syndrome can occur. There are three ways. Okay, 3 genetic paths that are there that lead to trisomy 21. First is primary or standard trisomy 21. Approximately 95% individuals have this. So every cell in the body will have 47 chromosomes. They have an extra chromosome 21. This occurs because of non-disjunction. Often they are linked with increasing maternal age. So a simple mistake in separation, they lead to lifelong effects. Next is the translocation Down syndrome that occurs approximately in 4%. Here the person or individual will have 3 copies of chromosome 21, but 1 copy will be attached to another chromosome, usually chromosome 14. The total count will be 46 instead of 47. But the genetic material will be having extra 21 material. So this is called as Robertsonian translocation. Okay. Now one of the fewer cases is mosaic Down syndrome. Okay, in mosaic Down syndrome, so here the cell will not have not every cell will have the extra X chromosome here. So some will have 46 normal one and others will have 47. So you might have milder symptoms. It depends on how many cells are affected here. So you have at the end you will have 2 population of cells, but they'll have one condition. And lastly, you have translocation carriers, which is a parent will sometimes the parent will have a balanced translocation carrier. So they have all the chromosome 21 material, but is rearranged in a different location. So they are healthy, but while reproduction, they can pass on too much of chromosome 21 to their child, so that can lead to Down syndrome. Okay, now children with Down syndrome, they have they have some recognizable physical features like gentle facial profile. They'll have almond shaped eyes, softer muscle tone, at birth, but this can be improved with therapy. Sometimes they'll have a single crease across the palm or slightly curved fingers. They'll have just small variations that make each person unique. Because chromosome 21 influences heart and immune system development, so they may have a higher chance of heart problems and heart conditions. But with early medical care and strong family support, they can lead a active, healthy, and joyful life. A beautiful part of trisomy 21 is that how it shows the diversity that is there in our genes and how the diversity adds to the world. Moving on, we have is the next to the other trisomies, trisomy 18 and 13, that is Edward syndrome and Patau syndrome. Edward syndrome is when a baby has three copies of chromosome 18 instead of two. Chromosomes 18, they carry genes that are important for okay, they might for early growth. So extra information can make development more challenging right from the start. Babies who have trisomy 18, they often have a very delicate appearance with small head and jaw, clenched hands with overlapping fingers, and tiny feet with a characteristic rocker bottom shape. Their organs also grow differently, especially the heart, which is why they may need extra medical care early in life. Trisomy 18 is more serious than Down syndrome because chromosome 18 has more essential genes. So the extra dosage places a heavier load on and a burden on the body. Even though challenges are significant, families often describe their babies as peaceful and gentle, bringing love and meaning in the short time they develop and share with them. The short time they share together. Patau syndrome, trisomy 30. Patau syndrome occurs when there is a copy of chromosome 30. This chromosome is involved in early brain and facial development. So additional genetic material can affect how the brain, eyes, and midline structures form. Babies with trisomy 13, they'll have cleft lip, small eyes, extra fingers and toes, and they will have some unique features as well. Why is that and most of the time they don't survive, they don't reach full term because because the vital genes are affected here. But the ones do survive, they do okay. They survive and cherish. They fight on their own way, and families cherish every time they have with they spend with their baby, no matter how short the journey might be. So why trisomy 18 and 13 is more serious than Down syndrome, trisomy 21? Trisomy 13 and 18, chromosomes 13 and 18, they carry more essential genes required for development. So this will lead to disrupting the multiple organ system development early in life. Very early, the organ systems will be disrupted. The development will be disrupted. So the body cannot compensate the reduced, so that leads to reduced survival. Many cases they end in miscarriage because of the severity of imbalance. The bigger the chromosome is, the more genes are affected, that leads to greater impact. Now moving on to much rarer trisomy, trisomy 8. Trisomy 8, here there is an extra copy of chromosome 8. The condition syndrome is called Warkany syndrome 2. And the cell will have, because not every cell is affected, so the impact it varies from person to person. So some children will have some mild features while others may require extra medical and developmental support. This extra chromosome 8 can influence growth patterns, joint movement, and bone development. So children may have long, slender limbs. They'll have unique facial features. They'll have deep set eyes. Some will have heart or kidney differences. Learning challenges will be there, but support can be given. But they will continue to learn, grow, and adapt with the help of supportive therapies. Full trisomy 8 throughout all cells usually don't survive early in pregnancy, which is why the ones that survive is the mosaic trisomy 8. So yeah, so every child with Warkadi syndrome too has their own strengths and story and shape their life in their own special way. We can't always cure chromosomal disorders, but we can treat their consequences more and more now. Okay, we can treat it more intelligently. Now, coming on to the cure and management treatment approaches. So, chromosomal aberrations, they affect the instruction book of the cell itself. So, most times we can't rewrite them. Instead, treatment focuses on two goals: when possible, to correct or to replace the faulty gene or the pathway, which is the cure approach, and in most cases, manage the symptoms or to prevent the complications and improve quality of life, which is the management approach. In cases of structural aberration conditions or disorders, like example hemophilia A, here the factor can be replaced. So you have factor replacement therapy for factor 8 and factor 9. So this can help to extend the life factors and the non-factor therapies as well. So you can have example, there are drugs that mimic factor 8 activity or rebalance the clotting. So you will need to have your injections, right? This is good. So gene therapy is another one which is emerging using viral vectors to deliver a working F8 or F9 gene in liver cells. So this allows the body to make their own factor for years. So we are now moving from lifelong injections here to one-time gene infusion, which can have near normal clotting for many years. For conditions like MCP2 duplication, neurodevelopmental structural syndromes, you don't have any true cure yet, but there are early intervention like physiotherapy, occupational speech therapy, symptoms control like anti-seizure methods, antibiotics for injection for infections, feeding support. Research are there into antisense oligonucleotides and gene silencing strategies, which are studied to turn down the extra MECP2 gene activity. You can also there are complex structural syndromes. So for complex structural syndromes, our best treatment is for supporting the brain muscles communication, and the research is exploring ways to how to dial down overactive genes. For Philadelphia chromosome and CML, the perfect example of precision therapy for a aberration, for a structural aberration is this. So we have BCR-ABL tyrosine kinase inhibitors like imatinib and newer agents. These specifically block the abnormal fusion of the protein created by translocation. So here, knowing the extra chromosome swap gave us a designer drug which turns off the cancer signal, turning a once fatal leukemia into a controllable chronic disease. Numerical aberrations. Here, for numerical chromosomal disorders, we can't remove an extra chromosome or add a missing one in all cells yet. So treatment focuses on early detection and multidisciplinary care and lifelong monitoring to prevent complications. For sex chromosomes like Turner syndrome, growth hormones in childhood, growth hormone in childhood, it helps to improve final height. Estrogen and progesterone replacement helps to induce puberty, maintains bonds. Cardiac, renal, thyroid screening helps to treat problems early. Infertility options like egg donation, IVF. Klinefelter syndrome. In here you can have testosterone replacement, improve energy, muscle mass, bone health, secondary sexual characteristics, educational and speech support if needed. Fertility treatments are also there for men. In sex chromosome aneuploidy, we can't change the chromosome, but we can balance the hormones, support learning, and protect the heart, bones, and fertility. Trisomies, for trisomy 21, Down syndrome, you have early stimulation like therapies. You have physiotherapy, occupational and speech therapy from infancy, correct surgery for heart defects, gut malformations, cataracts when needed. Okay, regular screening for thyroid problems with hearing, vision, leukemia risk, and onset of dementia. All this can be checked. Inclusion in school, supported development, and supported employment and community programs. This will help. Okay, inclusion is what is more important here. For Down syndrome, the treatment is really just about removing the barriers and providing medical and educational support so abilities can flourish, and they can help them in involving in all employment and every factors of life. Edward and Patel syndrome is more severe trisomies. In many cases, the care here is supportive and palliative managing, so feeding, breathing management. Sometimes pain related surgeries are might be required if the family is choosing that. Surgeries will be there. So shared decision making with families are emphasized. Focus on comfort and quality of life. For trisomy 8 and all highly individualized it is. So orthopedic care, surgery for heart, kidney issue if present, developmental therapies, educational support. Now coming on to the latest and emerging scientific approaches. So we are still far from basically deleting any extra chromosome safely in a person. But the research is moving very fast now. Gene therapy, like CRISPR, has already allowed reality in deleting single cell disorders like hemophilia, and targeted small molecules, monoclonal antibodies. They can help turn off dangerous fusion proteins in cancers like CML. Experimental work in animals and cells is exploring chromosome silencing for X inactivation, like mechanisms to shut down an extra chromosome 21. So far, now our strongest tools are early diagnosis, supportive care, and precise medicines, which help us to work around the chromosomal change. The future may allow us to work directly on the genome itself, but not now. So we explored how tiny changes in our chromosomes help shape development, health, and to sometimes life itself. So chromosomal aberrations aren't just scientific events, they represent real families, real children, real futures. By understanding these genomic twists and turns, we are learning to unravel the mysteries behind genetic conditions, diagnose earlier, treat smarter, and support individuals with compassion, with respect. The more we learn, the better we are at turning information into empowerment, empowering families to make informed choices, empowering children to access care and opportunities, and empowering the future generations, and with hope that is shaped by science. So now let's move on to some of the myths. Let's hear some of the common myths that is there about chromosomal disorders. First myth is that chromosomal disorders are rare. It's not true. Fact is that they are more common than you think, especially sex chromosome variations and Down syndrome. So they're more common. They're more than common. And the second myth is that parents are responsible for from these disorders. This is a myth. The fact is that most changes happen during the early development stage, and it happens by chance. No one is responsible or no one is at fault. Myth 3, children with these conditions cannot live a good life. With support, which is not true. But the fact is that with support, healthcare, many individuals can learn, survive, and thrive a meaningful life. Myth 4 is that these disorders are inherited. That is not true, right? Most occur spontaneously and they're not passed down from parents. And the myth 5 is that they always affect the intelligence. That is not true. The fact is that just like everyone else, abilities will vary. So many have unique strengths too. So remember, and some have they have unique strengths as well. Children will have just like how everybody else have variations when it comes to learning and intelligence. Same is true for them. They do have strengths as well, and they do have learning abilities and intelligence too in a very unique and in a unique way. So you have to remember that chromosomal differences are part of human diversity. They are not a limitation. While we can't always change chromosomes, medical advances, therapies, and education can really improve the quality of life. When we replace fear with facts, we replace blame with understanding, and we replace limits with support and possibility. Empower yourself and others with knowledge. Join our life science lecture series. Subscribe for more fascinating genetics content. I hope you all like this content, like this topic. So yeah, please like and share and subscribe. Thank you everybody. We'll see you in the next.